Okay. We are starting to discuss today on a new set of membrane operation. We have been discussing until now mainly on systems that are related to separations. But I was already mentioning that today membrane operations are not just separation, molecular separation, but they can be membrane reactors, chemical transformation would be controlled in membrane system. But one of the areas more interesting today, because there is a fast growing and new opportunities are appearing every day, is the area of what we call membrane contactors. Membrane contactors is a system in which the function of the membranes is not to separate, is not to convert, but is just to optimize mass and energy transfer between different phases. These operations already exist. They are basic unit operation in process engineering, in chemical engineering. Distillation is a typical case. Crystallization is another case. Extraction, adsorption, are all processes already existing and very well known in any industrial process. No one of them until today is based in general on membrane system. So most of you are familiar with this kind of term, but the fact that we have the opportunity to redesign all these unit operation based on membrane system is relatively new. Some of these operations are becoming more and more popular. Membrane distillation is a typical case. Other ones are also in progress. Membrane emulsifier is another interesting case. We are developing a study membrane crystallizer, not yet at industrial level, but very interesting and important for the possibility to improve significantly this kind of operation. Basically, as I was mentioning, membrane contactors are systems where, in general, microporous membranes, no dense anymore. No membranes as in reverse osmosis, in gas separation, or in nanofiltration, etc., or in pervaporation, but just microporous membranes are used to promote mass transfer between phases. By the way, keep in mind that this system exists already in nature. Our skin is the best example of a membrane contactor. In general, the mass transport is related to the fusion process across the membrane pore, and the interface between different phases is immobilized at the pore by taking advantage of the hydrophobic or hydrophilic character of the membranes. So this is a general, very general definition of what we are talking about. By the way, you can find some years ago we wrote a book in this area, and you can find some general reference there. So the kind of membranes which we will discuss to clarify compared to the membranes that we have been discussing a few lectures ago are always this kind of membranes, microporous. So the solubility diffusivity mechanism is not part of the membrane system. And they can be hydrophobic or hydrophilic depending the kind of system you are discussing with. For example, most part of the system we are discussing are if a solvent is water, is aqueous system. So we will use basically hydrophobic membranes. They will be able to avoid the penetration of the liquid phase, the salty water in liquid phase in the membrane system itself, and only vapor is going across. Vice versa, you can also use hydrophilic when you are using solvents which is not water, and try to do the same story with different kind of membrane. Not yet much develop the non-aqueous system in membrane contactors, but it's an interesting research field that will grow significantly. We will discuss basically two of the major membrane contactors that are just growing significantly and where we have a specific knowledge and where research is in progress. Number one is membrane distillation. As I was mentioning before, Distillation is a very basic system present in most part of the separation, that thermal separation that people are developing today. Not too much is still present as membrane distillation based on membranes, and you are more familiar with distillation towers where you have evaporation, condensation across the different plates of the column. In membrane distillation, the same kind of phenomena take place at the interface between liquid and vapor phase, which is the mouths at the entrance of each pore. Instead of having 1,000 different plates in the distillation column, we will have billions of pores across your membranes. It's quite interesting to remember because all these properties are very consistent with the basic property of process intensification. Flexibility, modularity, automatization, remote control, very low footprint are all present here. And here is one example that one single membrane contactor units, this is already developed at industrial level, it's called a liquid cell. It is basically the same units with the same hardware can be utilized in distillation, in emulsification, as the gas liquid contact extraction, etc., or in crystallization. So the hardware is basically the same. Not so easy, but in principle it is. The software to operate these membranes as a crystallizer or emulsifier means that the operator has to be very smart. He has to know the software, the system, and how to change different driving force, operating conditions for making an emulsifier instead than a crystallizer. And this is very, very consistent with the basic properties of process intensification that we discussed at the beginning. Here are listed the most traditional contactors that we are studying today. And as you can see here, membrane distillation is one. In membrane distillation, what you have is basically a membrane, microporous, hydrophobic membranes, able that making contact a liquid phase and a gas phase or another phase on the other side that can be also liquid, can be vacuum, can be gas. Driving force normally is a delta T, is a difference in temperature across, small difference because this is a porous system. So if you have to move the gas across, this resistance is relatively not very significant. So that can be a typical example of a case in which there is interesting opportunities to realize also on large scale the same units. And the limit that you have to the mass transfer is just the different resistance in the boundary layers on the feed side, on the permeate side, and in the membrane itself. Let's anticipate that we will see that one of the drawbacks in membrane distillation is not concentration polarization as we discussed in reverse osmosis, for example, but will be temperature polarization. So this is another kind of polarization that can really affect significantly the performance of your system. Colleagues or PhD students today in different parts of the world are just studying and developing modeling and understanding membranes more appropriate for controlling temperature polarization. And that's a significant important area of research for the future. There would be a modification of membrane distillation we call osmotic membrane distillation, in which we have a significant difference in the concentration across our membranes. You can realize the osmotic gradient, and that's something similar what we call forward osmosis. We have a draw solution on one side, very high concentrate, that will be able to move water across your membranes. And in some case, for some specific application, osmotic membrane distillation is useful because it is improving the performance of membrane distillation itself. For example, when there's more one volatile present in the feed solution, and you want to avoid this volatile going across together with water, you can use osmotic membrane distillation. We will mention why this. What's interesting that this system can be developed if you understand the mechanism to membrane crystallization. Membrane crystallization is nothing more for what concerns the hardware, they're the same units, basically. What you have to do is to concentrate to the point that you induce the formation of a supersaturated solution on the feed side. And if you have a supersaturated solution, you can induce crystallization, heterogeneous crystallization. Quite interesting, and people in crystallization now are studying carefully. They are learning about membrane very quickly, because for them it's totally new way to produce crystals. And you know, crystal is one of the most popular final formulation of most parts of the product that you have on the market. If you're looking how people are producing pharmaceuticals, food, etc., how you purify most substance, crystallization is one of the most way of doing. You know, the final formulation, normally products you produce are I don't know, emulsions. You will see also membrane emulsifier, or crystals, or different kind of powder, but crystallization is one of the most interesting one. So if you can develop a new system to crystallize product, quite interesting. You will see that in principle membrane crystallization is overcoming a lot of the limits of traditional crystallization, or traditional crystallizer. For example, we are able to crystallize specific polymorph of your mixture. You know, normally most product appears in different habits when they crystallize. Amino acid, you can have glycine. Glycine can be alpha form, gamma form. And the same for most part of the many products. Very difficult to decide a priori when you start which kind of polymer will be in the final product. Normally it's a mixture. With membrane crystallizer, we have been learning which parameters can induce the formation of alpha form instead of gamma form. And this is significantly growing, not yet on very large scale, but quite interesting. You will have other kind of contactors, the gas-liquid membrane contactor. You can extract and supply gas to a liquid. Membrane emulsifier, another very important final unit operation for the formulation of a lot of product. You can also control with membrane contactor the phase transfer catalysis. So there are quite interesting opportunities for doing this. Which are the motivation for trying to develop this kind of system when the system already exists? Because you can crystallize without membranes. You can emulsify without membranes. Why you have to develop this? Rule number one, as I was mentioning before, most part of the unit operation based on membranes are realizing the strategy, the principle of process intensification. So they are just system very compact, very flexible, with very low footprint. They don't induce too much side phenomena. Environmental impact is minor, etc., etc. So that is rule number one. So independent from all the other motivation, it makes sense if you believe that tomorrow most part of the processing will be based, will require to satisfy process intensification. That is motivation number one. It's very consistent with process intensification. However, there's more than this. For example, most part of the membrane contactor has a very high interfacial area for volume units compared to normal solvent extraction, for example, or to normal distillation or emulsification system. Reduced size of the module, wide range of operating flow rates, very flexible in the range of operation. They can operate at very low operating temperature. Distillation, normally in the normal distillation is approaching 100 degree, 90 degree, 120, depending the pressure, etc. In membrane distillation, you operate normally at 30 degree, if you like, 40 degree. If you want to increase transmembrane flux, you can go to 80 degrees at most, but it's not really necessary. So you can make the same operation, but at low temperature, which is very important for food application, for biotech application, for drugs production, etc., etc. In general, low operating cost, low equipment cost, and pretty safe, no high pressure, no high temperature, etc. In principle, membrane distillation has about 100% rejection. We will see the basic, there is no salts that pass to the in-gas phase. There's no, compared to reverse osmosis or nanofiltration. Rejection is always a ratio between concentration upstream and downstream. In membrane distillation, that is theoretical 100%. No sodium chloride will go in as a vapor. Only water is going in a vapor phase. And also here, you can combine easily separation and conversion eventually. Very flexible, show before, automatization, possible remote control, modular. Membranes are becoming more and more well done today. We have good hydrophobic microporous membranes with polymer. Basically, they are amorphous perfluoropolymers. Years ago, there was no real membranes appropriate for this kind of operation. Still today, most part of the membranes we are using have not been designed for membrane distillation or for membrane crystallization. They've been designed for microfiltration, for ultrafiltration. In this department, people are working under contracts to produce from this polymer some microfiltration or ultrafiltration membranes. But we know now that the same membranes eventually, with a better design, can be utilized exactly the same in crystallizers or in distillation. And that's very important again from industrial development. In general, we don't have traditional membrane fouling. There's no big convective flux to the membrane surface. In the system, there's no delta P or delta T. So there is a problem much less severe if you look to the traditional fouling problem we discussed last time. But if we are looking to the system, you will learn that there is new form of a fouling that we have to take care. For example, the membranes has to be hydrophobic, microporous but hydrophobic. If anything can induce a decrease of hydrophobic characters and transforming from hydrophobic to hydrophilic, this is the kind of fouling that we have to take care. So that's why we are using, as much as possible, strong amorphous perfluoropolymers, which they have a very significant hydrophobic character, but also they are resistant to the chemical attack. Polypropylene is not the best one, for example, because polypropylene easily can interact with alcohol, surfactants, with different kinds of chemicals, and lose hydrophobic character, becoming hydrophilic. That means this is big fouling, you cannot operate anymore. So we have to look to some new polymers, or we have to find a way to restore very easily the hydrophobic character, or to make composite membranes combining material, some coatings, some very thin layers of very hydrophobic material, and they are expensive normally, so you can make a kind of a composite system. Some support, less expensive, some coatings just to protect the hydrophobic character. And I was mentioned before, not very sensitive to the polarization kind of phenomena. These are the advantages, and there are some more some other ones in the sense that this system can be applied to many different kinds of applications, and people are learning today, by the way, because it was a little bit not clear in the past. One that is not listed here, but is listed when you're talking about the temperature. If you go in a place where people need to make fresh water from the sea, desalination, as in Saudi Arabia, you will learn that today in that country they are using a lot of energy coming from burning oil. 15 million barrels of oil are burned to produce water for the kingdom in Saudi Arabia. And that oil has significant cost today, and that's why they're losing a lot of money for production of water. And this problem is becoming more and more severe because this water is not only for giving to the people or in agriculture, but today there is what is called produced water. The water coming from the petrochemical industry, for the extraction of oil from underground, oil or gases, the same story, where for different reasons we have to induce what is called enhanced oil recovery. You have to push oil and gas to the surface by injection of gases, CO2, or injection of water. For each barrel of oil that you want to extract, today we need about 5-7 barrels of water. There's a ratio 1:7, 1:5, and this ratio is going to increase more and more because the quality of the oil and the gas is becoming worse. And you have to go underground, you have to penetrate in the sun, etc. Very complicated. A lot of water is going to be used in this way. That means we have to find a way to produce water in a different form using less energy. Membrane distillation can operate at low temperature, which means you can operate using solar energy. You don't have to warm up burning oil. And that's one of the reasons for which all around the Middle East, if you go in Saudi Arabia, if you go in Kuwait, if you go in Masdar, in Abu Dhabi, in Oman, etc., you will find people working, studying, developing, testing units of membrane distillation, trying to overcome the limits of. If you're talking with your people here in Korea, Dosan, which is #1 in the production of desalination plants, traditionally thermal system, Dosan is looking carefully and is trying to understand, develop what is going on in membrane distillation, not only in the traditional system anymore, because in prospective, the water industry will be much more related to membrane distillation than today. I was mentioning that these are the benefits, but where are the drawbacks? And there are some disadvantages that we have to take care. For example, as always, we need some pretreatment. Pretreatment is always necessary in any kind of membrane operation. I told you, if people are telling that you can just supply the feed, any feed to your membrane with no pretreatment, normally that is just, no, they're joking. We have to be careful about the pressure that you apply on the system. We don't need really pressure, but in a complicated system, in a big module, you can have pressure drops. Pressure drops across the system when you have your water flying on the membrane surface, etc., with your cross-flow system, your cross-flow water, you can induce pressure drop across the membranes. This is a problem that you have to keep control, because if you are increasing too much pressure drop, you are pushing liquid water across the membrane, across the porous system. The hydrophobic character is valid, it has to respect some law. That means it's related to the surface energy, to the size of the pore, etc. And so if you just apply high pressure, you can also move the liquid across. No more distillation, but just microfiltration. If you do this, rejection, is becoming, it's going down, or liquid phase is going across. Seawater is moving across your membranes, so does not work anymore. So you have to control the operating pressure. You have to keep control of the hydrophobic character, as we mentioned before, or hydrophilic if you're working with hydrophilic system. And for sure there is also a resistance related to the presence of these microporous membranes, which have a certain thickness, etc. This resistance normally is not very high, I was mentioned before, because the system is very porous. The porosity of these membranes is one of the major objectives you want to study and to understand. Increasing the overall porosity is a way to increase transmembrane flux. Average today, we have overall porosity of 70, 60 in some case, 40 in some case, some industrial membrane. But if you want to make better, 4 MD, you have to go higher. You have to go to 80 and eventually 90. When you increase too much the porosity, you are losing mechanical properties normally. So you have to optimize your system and to realize how to do this in terms of kind of polymers, kind of morphology of the polymers, etc., etc. Keep in mind that we understand from this, what we have been telling until now, that you will see there is some law that we have to respect, in which you can calculate what we call the penetration pressure, the pressure that you don't have to overcome, because if you overcome this pressure, liquid will go through. The equation that control the penetration pressure are related to the size of the pore, which means when you make your calculation, you say this membrane is 0.2 microns in porosity. Now you know that in your system, when you prepare membrane by phase inversion, Alberto Figoli was not showing you, but the pore that you are producing are not all equal. You always have a pore size distribution when you use phase inversion. And when you say 0.2 microns, this is the average value, and the most part of the pore will be 0.2. But always you will have pore 0.5, 1 microns, and eventually also lower value. You have typical balsam distribution in phase inversion, which means that as much as possible you have to try to realize a very narrow pore size distribution. Otherwise, for example, if you want to use this system for ultra pure water production, for biomedical application or the electronic industry, where they need to be sure that the water has ultra pure value, if there is one or two pore bigger, such a way that the penetration pressure is much low, so liquid can go through, you kill the process. That's why some of your colleagues all around the world today are just trying to work more and more how to reduce the pore size distribution and to produce membranes as much as possible with very, very strict, very narrow range of pore size. There are new methodology for doing this, expensive, but they exist. There is new way to produce tips that some of your colleagues are utilizing in this department, is one way to reduce the pore size distribution and to try to obtain as much as possible very narrow one. And that is an interesting result that you can have. But tips has some other problem. That means you are using polymer with solvents which are not traditional solvent, and so that is an area where a lot of work has to be done and is in progress. I was mentioning before that for each one of the membrane contactor that we are going to we mentioned, and the one that we will discuss in particular as membrane distillation, membrane crystallizer, you have a very well established alternative way of doing, traditional way of doing, conventional. So when you want to introduce new technology, you must have some strong motivation. You have to convince the people that this new technology really give you some benefits. Otherwise people say, well, you like membranes, we know about, but we don't need to change what we have been doing until now. You have to show them that there are some motivation for changing. There are good reasons for trying to have a different way of doing, and slowly people are learning and understanding. So I was mentioning we will discuss basically on membrane distillation, and in this picture you have the basic principle of membrane distillation. We have a membranes with significant number of pore, and pore of certain size. Average value can be 0.1, 0.2 microns, 0.5 microns. That is a typical range in which most parts of the membranes today have been produced. On one side of your membranes, you have your feed. That means seawater, for example. In solvent will be water in this case. And on the other side, you can have another aqua solution, a solvent, water. You can have air gap. You can make a vacuum. You can have a sweep gas. So what's happening here on this side is that at a certain temperature, this membrane is hydrophobic. So surface energy and size of the pore are such that no liquid can penetrate. But at the interface between the liquid phase and the vapor, which is in the pore, you can have some typical evaporation process. That means some molecules will leave the liquid phase and we go in the vapor phase. So the liquid will not penetrate, but the single molecules in vapor phase can penetrate as normally. There is no surface tension that will remove just the single molecules. And so you can have some molecules penetrating. These molecules are the one of the component volatile in the solution. So if there is a sodium chloride, protein or iron, etc., you will not see in the vapor phase. What is going through in this case is just the water, if this is water and electrolytes. If here there are some other volatile, wine, you can have alcohol and water. In this case you must be careful because some other volatile, alcohol as a certain level of is volatile also can go together with the water. That's why in some cases we have to change the system to adapt to new situation. But for desalination, which is the major interest at the moment, you don't have this problem. So in principle, we can assume that if this is configuration, only water will go in vapor phase and only water will be collected on the permanent side. So that is the basic concept that we are trying to realize. So only the volatile compounds can evaporate at the interface of the micropore hydrophobic. They diffuse across the membranes and will be condensed or removed on the other side. How to realize this system? Already now there's a lot of new design. There's a lot of engineers that are studying how to realize this. There's much more interest and effort today in trying to realize this system than in traditional distillation. By the way, before going to see the different system, remember, sometimes in the literature there is confusion. People are making confusion between membrane distillation and pervaporation. Pervaporation has nothing to do with membrane distillation. Some people are calling thermal pervaporation. So that's just because there is a temperature difference. Membrane distillation and pervaporation have nothing to do one with the other. First of all, in pervaporation, you have a dense membranes. The same membrane you are using eventually in reverse osmosis or in nanofiltration. And what you have in pervaporation is nothing more than a solubility, diffusivity type of process, exactly as gas separation or in reverse osmosis. What is new that you don't only, the driving force and the final property of the system are not just related to the difference in the vapor pressure of the components across the membranes, but also to the permeation rates. So you have a combination of the vapor pressure difference across your membranes plus the properties of the permeation across the dense membrane system. And that is what is making interesting pervaporation for some application. And we will discuss it a bit if we have time also about pervaporation. But remember that pervaporation has nothing to do with membrane distillation. So when somebody tells you, but it seems pervaporation, you say, no. And basically you say, pervaporation is a dense membranes where vapor pressure and permeation are working together compared to normal RO. Membrane distillation is a system where mass transfer across is only in vapor phase. You have evaporation and just transfer across. Very different. And you are using microporous hydrophobic membranes, not dense membranes at all. I was mentioning you can realize this concept that we showed before already in different form. And new one will probably appear, and already now engineers and good researchers are studying how to optimize the system to overcome some of the drawbacks. For example, to optimize, we are losing today about 50% of energy that we are giving. Instead of using this energy for the evaporation on the feed side, we are warming up the polymer. So we lose about 50% of the energy in just this warming up the polymer, inducing eventually temperature polarization, nothing positive. Today, the system already relatively well understood and well controlled is what we call a direct contact membrane distillation. In this case, the permate is just water in a liquid phase, and this is directly in contact with the membrane on the permate side. So what you have here, you have seawater, fresh water here, and fresh water on the other side. So you have a liquid on both sides, and the transfer across the membrane is in vapor phase. But you already have liquid here, and you put a liquid phase in contact on the permate side. This is the most traditional, the first configuration that has been designed, the easiest one. You can have another system in which, on the permate side, instead of having a liquid phase, you can have what we call a air gap. You can have just air, and you have a condenser at a certain distance from the bottom side of your membrane. So here in the middle is air gap. So the membrane side, the permate side, is a condensing surface separated from the membranes by an air gap. Instead of having just an air gap, you can have another configuration where you're introducing a sweeping gas. That means here you just have a sweeping gas that is circulating, and this is helping to extract the water. So the vaporized solvent is removed by the sweeping gas, basically, instead just by... these two are quite similar, but another one which is the most interesting for some application is what we call a vacuum membrane distillation. Vacuum membrane distillation, you just create a vacuum. There is no sweeping gas, no gas, just vacuum. You have a vacuum pump on the permanent side, and again the condenser, a condensation plate at a certain distance from the membrane surface. This is an interesting case that people are studying and using because in turn the overall energy consumption in this case is the lowest one, basically related to the fact that on the permanent side we don't have any resistance on the permanent side. Basically there is no concentration profile, no temperature profile that can create some problem. So these are traditional four kind of system, and all of them have some advantages, as always, and some drawbacks. That's why we have already four. Keep in mind that, in fact, we don't have just four today. We have already about six, because some of them people are already introducing modification and trying to. This is an area where chemical engineers will have a lot of work to do in the next year when this plant will grow and will become big plant. For example, for what concerns direct contact membrane distillation, there's one of these situations that you have a low efficiency of heat utilization because we have a significant heat loss by conduction through the membrane. I mentioned it before. Instead, the heat that you are supplying to the system, instead of being utilized for the evaporation of the water, are utilized to warming up the polymer, and you create a temperature gradient across, and that is heat. That can be about 40–50% of the energy. In air gap membrane distillation, again, you have a low conductive heat loss with respect to the direct contact, so this is advantages, but you have a higher mass transfer resistance than in the MCD. For what concerns the strip gas, you just you combine low conductivity heat loss with a reduced mass transfer resistance. What is happening here is that the permeate is condensed on an external surface. You have a certain distance between the membrane and the plate in which the condensation takes place, and after you have to remove and to recollect, and that is a cost that you have to consider. In the vacuum, for example, as I was mentioning before, we have a negligible, very, very low conductive heat loss through the membrane. This is relatively not very important. However, in this case, the membranes are very sensitive to any problem of wetting. Wetting means that your hydrophobic character can slowly disappear and becoming hydrophilic. And that can be a problem that you have to solve. Just to mention shortly that already now, when you are looking to the gas air gap membrane distillation system, there are some modifications. For example, there are people in Germany at the Fraunhofer Institute for Solar Energy where they are developing a system in which they are introducing a third channel with a non-permeable foil. Membrane foil can be polymeric, can be also metallic, in which you can realize a condensation and recovery of the heat that you are losing during the evaporation in the system. So that is a kind of system which heat recovery, part of the heat you are losing, is recovered in the system, in the module itself. And that is a way just to introduce some better performance. This system really is working nicely in terms of heat recovery, but if you look real life, you will realize that at the moment what you gain for the heat recovery system, you lose in the transmembrane flux. The overall transmembrane flux is going down when you have this kind of configuration with this third plate, and the recovery of the heat is just is not completely positive if you're considering that you are losing transmembrane flux, to the point that this big module are still under study. A lot of people are looking to, but if you want to find the real plant, you don't find them because some work still has to be done. That's the way in which they realize this kind of concept can be realized in this spiral wound system, in which you can just introduce this condenser foil in the system where you just condense inside the module the water that is going through. But that is a typical example of how you can realize in a spiral wound system with a different configuration compared to traditional one, in which you have the hot zone are in the center in the module. These cold zone are just on the external part of the module, and so you just reduce as much as possible the dispersion of the heat in the environment, basically. However, is an example that what can be done, but it really is not yet realized on large scale. And there is some other configuration of this kind. For example, some of you can, if you go in the literature, you will find some other example in which people are trying to realize in membrane distillation units the same cascade system you have in normal distillation. They put different cascade. Just instead of having evaporation condensation in a plate, they put different chambers with the membrane where you evaporate and you condense. You evaporate, you condense across the membranes, and you reproduce the same configuration of a traditional distillation tower. So there is different ideas just to try to develop as much as possible, but no one of them has been yet transferred on large scale, basically. You will receive, I think Nazer will send you one review recent for a few months ago on membrane distillation, maybe you receive already, where you will find a lot of reference related to what we are discussing. And more of this, if you are interested in membrane distillation, you will receive also a link, a reference on what is called a virtual issue on membrane distillation of the journal Membrane Science. So we made a kind of survey, everything published in membrane distillation the last 30, 40 years, and has been summarized and has been listed, and we selected in about 200 papers, the 30, 40 that, on our opinion, are the most interesting one. And one of your colleagues, our PhD students in Italy, Amir, helped me make this virtual. So you can find everything on membrane distillation published in the journal Membrane Science in this virtual issue. So you don't become crazy, and you can just look and everything is there, and that is a nice summary. And also the paper, the review paper that has been published a few months ago. Which are the driving force to mass transfer in a membrane distillation unit? So basically, the transmembrane flux is always proportional to the difference in the partial pressure across the membrane. So we have the traditional equation that now is very familiar to you. So the flux is proportional to a term that is a term of proportionality that can be function of temperature, pressure, composition, structure of your membranes, we have to define, and the driving force is delta pi. Keep in mind that this relationship can be written a little bit more carefully, because this pi is just your partial pressure, but the system in which we are working very rarely will be a system that where the equation will be written in terms of it's an ideal system. The probability that we are working far away from ideality is very significant, and to the point we are using normally membrane distillation to concentrate water and to crystallize. So we are going to very high level of concentration, and we just have to consider that the system is not ideal, so we cannot use this kind of equation. We have to introduce a activity coefficient. The activity coefficient in a very high concentration is something that is not obvious, and that you have to find the appropriate level of deviation from ideal character. This is important in membrane distillation, because if you are just using ideal value of the vapor pressure, the driving force of your process can be significantly affected by errors, because you just want to calculate the driving force of the system, the amount of water that will go in a vapor phase, and if you don't use correct expression where your vapor pressure is related to the molar fraction through an activity coefficient value, you make significant mistakes. The relationship between the vapor pressure and temperature is, I think, is very well known to you. It's not linear. Clausius-Clapeyron equation, and just to remember, that is an exponential behavior, which means that when you are working at a low vapor pressure at low temperature, you have a relatively linear variation with the vapor pressure with the temperature. But as soon as you increase a little bit, this is becoming exponential. That means you have much more vapor going in vapor phase when you are increasing temperature, and there is no linearity. And that's when you make experiment, you will check by yourself immediately this kind of behavior, which is very, very important. In fact, the transmembrane flux that you have with increasing temperature will have always this kind of behavior, will be exponential, will be not just linear at all. And in any experiment you can check this, and you have to expect. And if you have a linear behavior, something is wrong in your system. You don't have a vapor phase taking the mass across. You can have some liquid going across, etc. So it's something that you have to check and to expect. Careful that there are some other deviation related to the traditional equation that you are using, because at the entrance of each pore that you are considering, the liquid phase is not flat, but you have a kind of curvature for what is considered the vapor-liquid interface. And there are equations, the Kelvin equation, that just give you the possibility to correct, to obtain the correct vapor pressure, taking care of this curvature. And that is, you see, is a function of the radio of your pore. So depending if the pore is becoming bigger or smaller, this deviation from the ideal character is changing, is a question of the surface energy and the liquid molar density. So all these parameters are present in the Kelvin equation. So the normal vapor tension is not the traditional one, but when you have a pore, a system, a porous system with size of the pore of the order that we know at least 0.2, 0.1, so it's not very, very small, you have to calculate the vapor pressure with using a correct equation, not assuming that there is ideality. Here, just to give you an idea of the complexity, for example, activity coefficient. If you want to know for all your solution and eventually for your mixture, normally you don't work on a single component solution. It's not just water. It's water plus salt. And normally not one salt. It's water plus a variety of different salts. So if you want to have a correct value of the vapor pressure in your system, and you have to assume that there is an activity coefficient of the system, not easy to have. It's not only one answer. You can have different kind of relationship of the activity coefficients in terms of the Gibbs energy, temperature, and other parameters. And you can go in the literature, you find the Margulis equation, and you will find the Van Laar equation, and you will find the Wilson equation, and you will find another one. The most interesting one and easier to remember eventually is the relationship developed by the Debye-Huckel theory that I've been mentioned already a couple of times, which is assuming, trying to describe the behavior of any electrolyte solution where you have different ions, positive and negative. These ions don't exist by themselves. Each ion is covered by clouds of charge of different sign compared to the central one, and this charge distributed with certain Higgs, and it's called Debye clouds, and there is a level of Debye radio that you have to calculate, and these clouds control the interaction between different ions. The different ions don't attract or reject one from the other in terms of their size and charge, but you have to modify in terms of the clouds of charge of different signs that are around. And this is creating a deviation from ideal character, activity coefficient. For doing this, you find the relationship is interesting, where you can introduce the activity coefficients that we have been mentioned before are related to what is called ionic strength of your solution. I already mentioned this when we spoke about the Donnan effect, etc. And the ionic strength of the solution is nothing more than the addition of the charge of the overall solution for all the different ions, concentration multiplied for the square of the charge of the single ions. So this is the overall ionic strength of your solution. So if you have a monovalent salt or a monobivalent ion, etc., the ionic strength is changing. So it does not change only the molar concentration, but just before the real deviation from ideal character that you measure through the activity coefficient is changing as a function of the product of the molar concentration for the square of the charge of the single ions. And that makes a difference in the deviation from ideal character. This is a more clear equation to remember, and you can have experimental, you can see deviation from the activity coefficient, for example, as function of the molar concentration for sugar solution. You can see here there is significant deviation, increase the concentration. It's not constant for sugar, it's not linear for sugar. The situation is a little bit complicated. That means that when you want to make calculation for big plants and you want to know exactly your driving force moving the water vapor across the membrane, etc., and you need to know exactly which is the activity coefficient of the solution that you are going to concentrate on one side of your membranes. Mass transfer across the membranes, is related to the mass transfer coefficient, basically is related to the different kind of resistance that you will find in the system. We discussed already a little bit before, but in this kind of system you will have a mass transfer coefficient for the resistance on the feed side, in the membrane itself, on the distillate side. So these are for sure the three mass transfer coefficients we have to define and to introduce in our general equation before. And you can visualize in this form. Basically, you can have a boundary layer resistance on the membrane surface on the feed side. You have a kind of boundary layer resistance on the permeate side of your membranes. You have a viscous resistance, the membrane resistance, which is the viscosity in the pore of your membranes. Do we have something that works? Let's see if it's better, this one. Okay, perfect. So we have a viscous resistance in the pore of our system, and we can have Knudsen resistance or molecular resistance or surface resistance. Normally now, when we are working with the membranes with a certain level of porosity, 0 to micron, etc., this surface resistance is, in first approximation, negligible. You can cancel this situation. And normally in direct contact membrane distillation and also in vacuum membrane distillation, the boundary layer resistance is also negligible on the side. So what is normally effective, what you have to consider is this Knudsen and molecular resistance in the pore. And normally, in most parts of the membrane we are using today, where there is a pore side of the order 0 to microns, and today we are working and assuming that both of them are present. So if you want to compare experimental results with the prediction, you have to assume that there is overlapping or integration of molecular resistance with nuclear resistance. That's one typical case. Now, if you want to study the important effect that we have been describing already in most parts of the separation membrane operation as concentration polarization, and you can use exactly the same approach that we have been using in reverse osmosis. If you do, you can just define the situation, the transmembrane flux you have in your system, and you can define a concentration polarization coefficient given by the different ratio between the concentration at the membrane interface and in the bulk. That means the concentration here and the concentration in the bulk. And also in membrane distillation, you can create some concentration profile. However, in this case, this change of concentration does not affect too much the driving force in your system. There is no big effect. There is no osmotic concentration that you have to consider here. So this effect is practically negligible, and is much more important eventually the increasing of viscosity when you are increasing too much the concentration. So in the first approximation, we are considering that the concentration polarization has a limited effect on the process performance, and that has been very well defined until now. If you want to find with some detail the different mass transfer coefficient we are discussing about, you have to, you can correlate through the Sherwood number, Reynolds number, and Schmidt numbers, and you will find different correlation present in literature that where people have been studying to try to describe the equation. And depending from the flow dynamic condition in which you are, and depending from if you are in a laminar, in turbulent, in tubular, the different geometry, you can find different reference of the people working membrane distillation. You can see here that there are each one of this kind of relationship that has been defined here, where you can find phenomenological expression for the alpha, beta, gamma. Alpha, beta, gamma are just the relationship that correlate Sherwood number with Reynolds and Schmidt number for giving your and where here is your mass transfer coefficient. And these numbers have been just phenomenological derived, and depending from the different situation and from different kind of cell, stereo cell, tangential flux, holofibers with helicoids that you have Coriolis acceleration that can control the surface concentration, or also some inclination, some profile on your membrane. You can have different kind of relationship. And here the effect that you can have For example, the mass transfer is a function of the feed temperature, and that is a typical expression. Again, you can find this linear relationship function of the concentration of the species that you have, going from 0.6 molar to 1.3 molar. There's not a big difference, to confirm what we were talking before. Across your membranes, that is the typical relationship that we have to consider. And now the point is, if we want to consider a viscous flow, Knudsen flow, or surface diffusion, etc., etc. And the traditional, you can introduce the definition of mean free path of a molecule. That is the average distance that the molecule have to travel between to have a collision with the surface. So there are situations, as you know, where it's much easier to have interaction with the surface and not between molecules, depending, that's becoming from the size of the pore. You can have a situation in which you have what we call a Knudsen diffusion, in which there is a predominance of the collision between molecules and the membrane walls, and molecular diffusion, in which the predominant collision between single molecules. This kind of process, molecular diffusion, it takes place, is prevalent when the size of the pore is higher. So if you go to pore of 0.3, 0.5, etc., you are going in this direction of molecular diffusion. If you are going to size of the pore much smaller, at 0.2, 0.1, 0.05, you are a Knudsen diffusion. And that makes a difference in the equation that are controlling the mass transfer across. And you remember that Knudsen diffusion, for example, there are equations that are where the small molecules are moving faster, just because there is a predominant, and the bigger molecule stay behind. And that is what is called the Graham equation that you are using to separate molecules. So this kind of system can be different. In general, with the size of the molecules we have today, with the size of the membrane we have today, the two things are normally present, they overlap. So that means that when you are writing your diffusive flux across the system, the overall flux across your membrane, you have to consider both the Knudsen diffusion coefficients and the ordinary diffusion coefficient, basically. And if eventually you have also to introduce the viscous flux, that means Poisson equation that is familiar to you, when depending from the size of the pore. So this is basically the different phenomena. And if you want now to utilize this equation, assuming that molecular diffusion or Knudsen diffusion for the different kind of configuration, vacuum, air gap, the ion contact membrane distillation, assuming some mean pore size, that means assuming which kind of system is, you have to take in consideration. For example, in this case, you are assuming for small pore size lower than this length, of the frequency of the collision with the wall, etc., is higher than the frequency between single molecules, the mean free path. And you have here just Knudsen diffusion. Here you can have the diffusion through stagnation air. You can have Knudsen diffusion and diffusion transition, and you can have just Knudsen viscous flow. And at the end, each one of this kind of system will give you a different kind of relationship, utilizing the different kind of equation. All this, at the end of the story, is important, not very important, because the change in the resistance that we have in the system at the interface, etc., does not affect too much the overall transmembrane flux. Concentration polarization is negligible. It means the concentration has not a big effect. What is more important is the heat transfer, which is related. Until today, people work in this area trying to understand more. We always assume heat transfer and mass transfer totally independent. We don't put any relationship because it's becoming too complicated to solve the equation. However, keep in mind that there is a lot of space for improving the simulation modeling of the overall transport phenomenon across our membrane distillation system, where you start to integrate, to combine together the heat transfer with the mass transfer. Because it's true that the mass transfer does not affect too much the driving force, but concentration polarization can affect not the overall mass transfer in principle, but the heat transfer. Because the heat transfer can be significantly affected by the changing of the mass transfer also. Until now, if you go in the literature, you'll find the model describing one or the other phenomena, not together. It's not easy, that is the reason. But we know that heat transfer can really kill your process. And that's why it's important to understand how heat transfer can be related eventually to a concentration polarization phenomenon. Heat transfer is the same story, and here you have that the overall total heat flux across your membrane is related to the heat transfer coefficients in the boundary layer upstream, heat transfer coefficient of the boundary layer downstream in your membrane, and what is happening in the membrane phase. Now in the membrane phase, as we are already discussing before, we can have a different kind of heat transfer. We can have the one by vaporization and the one by conduction. That means part of the heat that you are supplying to the feed side of your membrane is just utilized to vaporize your molecules and putting them in vapor phase through the delta. That is delta H of the evaporization step. But part of the heat can be just utilized to warm up the membranes, the polymer. And that's we don't really looking for. That is a problem for us. So the principle should be to have, for example, materials with a very, very low thermal conductivity, such a way that we can minimize any heat warming up of the polymer. But that is the situation that we have. And so you have to, if you want to know the overall heat flux across your system, you have to know all the different mass transfer coefficients. And again, this is the situation. So you have a thermal boundary layer resistance. You can have a thermal boundary layer resistance on the permeate side, on the feed side, where what concerns the membranes, you have the heat transfer is related by the conduction and by the latent heat of vaporization. So these two terms have the one. The one we are more interested is this latent heat of vaporization. This one, really, we are not interested. If we can avoid, should be nice. Not easy, but that is the situation. Also in this case, keep in mind, the phenomena we are discussing is totally different from the phenomena we've been discussing in concentration polarization. As you remember, in concentration polarization, what is normally happening is that the concentration at the membrane side is going up. You accumulate some of the solutes that are not crossing the membranes because the water, the solvent is going out. So you increase the concentration. And so you have an increasing of the concentration at the membrane interface. What is happening here is just the opposite. Here you have the temperature that you are supplying, that you are assuming 100% useful to create delta T across the membrane and moving the mass across, is just going down because you utilize part of this temperature, heat is for the evaporation. And so you just use in the right form. You're spending energy to evaporate, and this vapor phase is going across the membranes. But the other one is also you are just warming up the polymer, and we don't need this. So if you don't keep control of this temperature profile, you are decreasing two things, very important. One, you are decreasing the number of molecules that from liquid phase go in vapor phase. Point number one. Second, you are decreasing the delta T necessary for moving these molecules across. Delta T can be very small because this is a porous system, so you don't have big resistance. However, is a loss of driving force. So this phenomena can kill completely membrane distillation if not well controlled. Exactly as the same that we discussed when we were discussing reverse osmosis. And you will find in your notes, if you don't take care of the concentration polarization, seawater is going across your membranes and you are assuming that there is a pore. It's not. It was a wrong operation that you have been carrying on. You are not keeping control of the concentration at the interface. So the membrane was working with 99.9% rejection against a solution that was not seawater, 0.5 molar, but was the interfacial concentration that was 3 molar. And with 3 molar, seawater is going across with 99% rejection. Same story here as final results. So you have to keep control of thermal polarization. Our PhD students today in Italy are mainly working on better understanding, better developing, better measuring the cell with 16 electrodes all around to measure the temperature profile that you create across the membranes. It's not easy, but that's what has to be done. In fact, here you can have the evidence of the temperature polarization coefficient. You can see here 0.2, 0.4. In some case, you are approaching the good one, which is the ideal case. But normally, we are pretty far. And this is a different condition. In case you see here, if you are having a stereo cell with Reynolds 8000, you have a 0.2. When you go to Reynolds 32,000, high mixing, etc., you improve to 0.4. Still not ideal, but that is the effect of the just stirring. Here you have a laminar, and if you change this different thickness, again here 0.15, 0.4, 0.7. That means when you are going with relatively smaller thickness of your membranes, and that is you can improve the concentration polarization control, and just still not approaching the ideal value, but much better than 0.15, and so on. That is the different level of Reynolds number can have an effect, and that is the typical case. Also, in this case, if you want to find the expression for your heat transfer coefficients, you can use traditional adimensional numbers. You can find the literature, the Nusselt number, the Prand, and the Grace number, and this one they will give you some possibility to evaluate the overall expression correlated the Nusselt number with the heat transfer that is here in the Reynolds through in laminar flow, in turbulent liquid, in turbulent flow, etc., etc. Also here you can see these equations are not the same. If you look at this equation, each one of these exponential, this term alpha, beta, gamma, each one, depending from the guy, from the reference, we forgot to put the reference, but each one of these is something different in the overall configuration, but also in the different experimentalists. People made experimental evaluation. These are all phenomenological parameters. You don't, there's no theory that you can develop. And this number, you can see that they are not too far, 0.33, 0.38, but basically you have to develop your own relationship. Okay. Again, there are some other terms that we have to consider very interesting here. And basically what they are is that we have been defining that the overall transfer across the membranes is related to the latent heat, to the evaporation of our molecules, and to the warming up of the membranes, that the conduction to the membrane material. And that means this is a question that we have to consider, and in fact the mass transfer coefficient has to be redefined, introducing all the parameters related to the membrane morphology. So you can see here that you have to introduce in a definition of your transfer coefficient this porosity, the thermal conductivity of the solid, the Ks here, and the thermal conductivity of the vapor within the membranes. Normally we are assuming the membranes are, when you start the operation, you made vacuum. There is no vapor already, but there is some vapor, and so you have to term the thermal conductivity of the vapor within the membrane has to be considered. And this is always related to the real empty space, the overall porosity. Again, porosity is not an easy parameter to define, because you measure, and depending from the tortuosity, depending from the morphology of the channels, these terms are not easy to predict. But these are the parameters that you have to control when you make your membranes. And you have been learning in the past discussion how much we can change the overall morphology depending what we need. That's why we are always telling that when you make a membranes, rule number one, which is the application you are looking for. Because depending what will be the end, the operation of these membranes, you have to change the parameters. And you have to look to change something in one case, something in another one. For example, if you're looking to this kind of application, membrane distillation, you have to take care for, first of all, for the thermal conductivity, because otherwise this term here will be would be a penalty for you. And we are moving from, we are using basically today polypropylene, PVDF, and Teflon. And you can see here, there's not too much, but there is a difference in thermal conductivity. And that means an influence on the 50% of the energy we are consuming, as I was mentioned before. That's why today people are studying new polymers and eventually also some hybrid membranes where you can try to induce change in thermal conductivity by making some composite membrane. You can have some fillers with they can change the overall thermal conductivity of the system. If you make this kind of membrane, that can be quite interesting for membrane distillation. Just to give an evidence here, how much this transmembrane flux can change with changing the membrane thermal conductivity. You can see that from depending from polypropylene, PVDF, and PTF, we have a quite interesting variation, and that's what is the thermal efficiency that also is changing. It means how much of your heat is going really to the evaporation or to we lose in the case. And that depends very much from the value of the Knudsen diffusion. That means how much we have molecular diffusion or Knudsen diffusion. And that is a question of the size of the pore, as we learned before. You can assume Knudsen for narrow pore, you assume molecular diffusion for bigger pore, and that depends how you make your membranes. So today, in the meantime, we want to produce membranes with high porosity, and so big pore. But big pore can be more molecular diffusion than the Knudsen diffusion, and that is something that you have to understand. Which one is more convenient for you? You want to have Knudsen diffusion or molecular diffusion? And that is one of the objectives in the design of this kind of system. And if you go in the literature, you will find that there is these phenomena are going through, well, they are not here, are never linear, we will see next time, are going through minimum or maximum. There's always some, but you can increase the heat, and in principle you are increasing transmembrane flux, but in this way you are producing some other problem in losing more part of the heat in the warming up. So they have always a question of optimization, and we will discuss this next time. Are we at the end? Okay. Well, we will continue on Friday with membrane distillation and membrane crystallizers. And just to remember what I was mentioning before, you can find everything will be in the notes, but there's one nice recent review and virtual ECO on membrane distillation where you can find everything about. Okay? So we meet on Friday.
Thank you.
Thank you. You already make a big books.